Greetings. The problem I want to solve for you now is an example of how to apply the mass conservation and the first law of thermodynamics to a system and also later on to a controlled volume. The problem is very uh, straightforward. It has appeared in one of my midterm exams, and now I extend it for a full solution and a full view. The problem is this. It says that we have a rigid tank. This is a rigid tank. This is a rigid tank. And this is rigid tank has a volume of V equals 1 cubic meters. It has a valve at the top, which could open and let steam out, or it could be closed and then should not let any mass out. Okay. The problem tells us that the initial condition of the steam inside the tank, so what we are dealing with is water. We are dealing with water. Initial condition. What is the initial condition? The properties are, we define a condition or a state with properties. Two independent properties are enough to define the state. And the two independent properties for the initial condition are P equals 1 bar, which is also equivalent of 100 kilopascals, and X equals 1%. These two are independent, and therefore they define the initial state, the initial condition. Then two processes happen to this tank, or to the steam inside the tank, to the water inside the tank. In the first case is just heating, just heating. This is what we do. We have a solid tank and we just heat it. The problem, if this was P1 and this was X1, for the second condition you have P2 equals 20 bars, which would be equivalent of 2000 kilopascals. Okay? This is the second condition. This is a very applied example, because if you throw a can into fire, then what happens? The can is a solid tank and its pressure builds up. If it can't stand that pressure, it will burst. Very dangerous practice, but this is exactly what this problem is telling us. Okay, so in the third case, is constant pressure. This is the second process, which is the constant pressure, and takes us to the third case. Valve is open. Valve opens and lets steam out, so that while we're heating, the pressure remains constant until there is no liquid in the tank. So at no liquid in the tank until no liquid in the tank. So whatever there is in the tank is only saturated vapor. Okay, so X2 is 100%. You see, this is the language of thermodynamics that you have to translate the description of a problem to. The problem tells us that there's water, some water in the tank. We heat it, and since the valve is at the top of the tank, some steam goes out. The valve is open and the heat is done such that the pressure remains constant. This is just similar to what you experience when you have a fuel, a canister that you use for your cooker or you use for a grill. The liquid fuel, the liquefied fuel in it is in saturation state. When you open the valve, some gas goes out of it, some, in fact, vapor goes out of it, but the pressure and temperature remain constant. Why? Because the canister, the cylinder, absorbs heat from surrounding so that the temperature remains constant. A constant temperature would also mean a constant pressure. The practice continues until all liquid in the tank has turned into vapor and then gone out of the valve. The practice ends when there is no further liquid in the tank and therefore the pressure starts to drop. Here, we say the problem tells us that at final condition P3, this is 3. At 2, we don't know, but P3 is also 20 bars, which is equivalent to 2000 kilopascals. P3 is 20 bars, X3 is 100%, and um, the condition is saturated liquid. Just to make it clear what we mean, it's good to draw a figure. And the figure would look like this. We have a TV diagram, we have a TV diagram, and this is the saturation line. There are two constant pressure lines. One is 100 kilopascals, and the other one is 2000 kilopascals. It always pays to know what the values are at the critical point so that we know if our pressures are above critical, lower than critical, or temperatures are. What position do we have as compared to the critical point? At critical point, the pressure is P equals 22064 kilopascals. So we are far away from the critical point with 2000. This is 22,000. And the temperature is 373.95 degrees C. Soon we shall see what the saturated temperature for these two pressures are. And therefore, we can compare them with whatever that happens um, with critical point. Also, it's good to know the specific volume at the critical point, which for water it is 0.03106 cubic meters per kilograms. And this is the critical point. We now know what the position of pressure lines are as compared to whatever happens at critical. And now to find the rest of the properties of steam at these two pressures, we need to go either to a table, which you would usually find at the end of all thermodynamics books, or you need to open an application on your cell phone or any other means that you know. You could use also EES for finding properties, but as it is, I would try to do it with um, whatever there is in a table. Now, this is a sample table, and what you find here is this is the 100 kilopascal line. Let's see. Yeah, this is the 100 kilopascal line. It is here, and okay, this is the saturated temperature, a specific volume at uh, liquid phase, saturated liquid, saturated vapor, and all the rest of the properties, UF, UFG, UG, HF, HFG, and HG, and all the rest are written down here. And also, if we continue the table to the 2000 line, 2000 kilopascals, which is here, we also have the saturated temperature for this pressure, and then a specific volume for saturated liquid, specific volume for saturated vapor, and all the energies. And what I shall do now is try to write down all these values on my paper. Well, these are all the properties that I've transferred from the table to my paper. These are all the properties that of steam, and regardless of what the problem is, these properties are steam properties. For example, uh, if we have for 100 kilopascal, we know that Vf is 0.0010143. It means that this point on this figure is 0.001043. That's clearly what it is. And for Vg, it is 1.6941. And I write cubic meters per kilograms here and degrees C here, so that would be valid for all numbers that I put on my figure. The interesting point is that the Vg is for a 2000 kilopascals. Vg, which is here, is 0.099587. What does it mean? This is about zero point 0.1 and this is about 1.7. This means that this point should have been 17 times further away from this point. If this is 0.1, this is 1.7 about, then this point should have been 17 times to the right as compared to this point. We haven't drawn the figure correctly, but let it be this as it is for the time being. Still, we shall know the difference and the role it plays. It also pays to learn from these numbers if the same happens to you. I mean, if I draw a figure, and I will do it here, I will do it just here. I have some room here to do it. And if this is a T and U diagram, how would the saturation curve look like in this figure? And you see, UG is 25.05 for 100 kilopascals, and 2599, which is even higher. Look, this was 16 times smaller than this one. This one is higher than this one. So the curve would look like this. The saturation curve would look like this. I mean, this would be 100 kilopascals, and the value here would be UG, would be 25 kilojoules per kilograms. The value here would be 2505.6. But if this is 2000 kilopascals, the value here would be 2599.1. You see, the shape of saturation line on the vapor side is totally different for a TU diagram as compared to a TB diagram. And the two diagrams differ. So we have to learn how the saturation lines show on different diagrams. Okay, now what we have to do now is to install our problem over these curves, because these are steam properties, nothing to do with our problem. To draw these lines up to now, as it is now, I have said nothing about our problem. But as it is now, we have a point 1, which is here. If our point 1 of the problem is on 100 kilopascal line and with 1% quality, and it as neither the mass changes nor the volume changes, then the specific volume remains constant. I will explain this further later on, but it's pretty straightforward to understand that when it is the rigid tank, the valve is closed, neither the um, neither the volume nor the mass changes inside it, and therefore specific volume remains constant. Therefore, this would be point 2, and this would be point 3, which is the uh, saturated vapor point. These points are drawn on a TV diagram, and they have two processes. You have two processes. Process 1, 2, which is a rigid tank, closed tank, mass remains constant, volume remains constant, and process 2, 3, which is constant pressure process. What happens is that some steam is let out. You see, heat is absorbed, but some steam is let out, until there is no liquid on the inside the tank. Look, it's very important to note that no mass is inside this curve. Okay, all vapor are here, all liquid are here. I mean, if you draw a line here, which is liquid is here and vapor is up there, this is vapor and this is liquid. Okay, all liquid is here and all vapor is here. There's nothing in the middle. Okay, if we mention a point like this or a point like this, uh, these points are just averages, average assumptions. They're not physically viable points because all liquid is here and all vapor is here. Now we have shown our problem over a TV diagram. In fact, the TV diagram was there for STEAM regardless if you had a problem or not. Now we have installed our problem over this diagram and we are in a good position to calculate properties of point 1, point 2, and point 3. I shall solve the rest of this problem in our next video. Cheers.